When we refer to the oxidation number of an element, what we're really referring to is we're looking at how many electrons are likely to be gained or lost by an element in order that it might obtain a more stable electron configuration. Now, a lot of times the oxidation number will match up with the charge that we associate with ions that are formed by these elements. But the driving factor behind why do some elements gain one electron, gain two electrons, lose one, lose two, lose more than that, has to do with what's its configuration to start with and what would it need to do in order to obtain a configuration that is more stable than its natural state. When we talk about these oxidation numbers, particularly when we get into the center section with the transition metals, we know that if electrons are going to be lost, if an atom is going to ionize, the first place those electrons come from are the outermost valence shell electrons, which for the transition metals are always going to be s electrons. Okay, before we get into the D block, we always start the next higher main energy levels as sublevel. And so those are the first two electrons that will tend to go. Beyond that, then, there's the possibility that the D electrons, which are not typically in the valence shell, but if they become the valence shell due to the loss of the s electrons, then they may also be lost and thus contribute to additional oxidation numbers that we see, particularly for the transition metals. So again, some atoms, particularly transition metals, will tend to have more than one oxidation number. As a review, whether or not the oxidation number will be positive or negative depends on what's happening with the electrons. If the atom is going to gain electrons, then they'll have more electrons than they do protons, therefore you would overall have a negative charge. Conversely, if the atom is going to lose electrons to become a more stable configuration, then it will have a positive charge. The number that's associated with the oxidation number is related to how many electrons were either gained or lost in order to achieve that level of stability. So when we talk about stability, how do we know what a stable configuration is going to be? Well, the epitome of electron stability is to have a completely filled, not just sublevel, but valence shell. And so when we think about the elements that naturally have the valence shell, the most stable elements of all, those would be the noble gases. So if any atom is going to either gain or lose electrons in an attempt to become that most stable arrangement, the most stable it can be, it's going to try and achieve that full octet. Now for elements that might be close to a full valence shell, like your alkaline metals or your alkaline earth metals, maybe your halogens, the chalcogens, the oxygen family, there may only be one oxidation number for those elements because they're so close to that epitome of stability in terms of configuration that that's the only choice that they're going to have, that they're going to work with. But for elements that are a little further away, particularly in the center of the table, the transition metals, getting to that full octet may not be a reality. It may not be energetically favorable to be able to lose that many electrons or to tack on a bunch of electrons to get to the next full octet. And so what happens is that when those elements react, they may react in a way that will, first of all, lose the valence electrons, but then lose a certain number that may end up with, say, a half-filled D sublevel, or may completely then empty out the D sublevel. So there's a lot of times options, particularly in the transition metal section. And what you see here is kind of a hierarchy of the different levels of stability that we get. The full octet for the valence shell, a filled sublevel. The benefit there is that you have symmetrically filled orbitals, completely filled orbitals in the entire sublevel, and that could be any sublevel, SP, D, or F. The half-filled sublevels, according to Hund's rule, you've got one electron to each empty orbital. So what you have is symmetrically filled, half-filled orbitals. And there's a certain level of stability that is associated with those symmetric fillings. So when we think about the elements of the table and we consider their electron arrangements, their structure, we can see for instance, the alkaline metals, they all end with an S1 configuration, which means they are one single electron past a noble gas core configuration. which is the epitome of stability. So those elements are super likely to give up their electron in the process, becoming a positively one charged ion, which has the same configuration as your noble gases. So it's very favorable for them to do so, and thus the alkali metals all have a positive one charge and only a positive one charge. Hydrogen sits above that group 1 family, the alkali metals, but it's generally not considered a member of those. Structurally, it ends in S1, but its properties don't match that of the rest of the alkali metals. Generally speaking, any element that's in the same column as another, when they're in the same family, they're going to have similar properties, similar behaviors, similar bonding patterns. And that's the case because of the similarities in the valence electron structure. The next family over, the alkaline earth metals, all of them in an S2. Now S2 is a filled sublevel, so you might think, well, there's a certain level of stability there, but they're so close to being able to have that full octet arrangement, or that filled valence shell arrangement, that it's still pretty energetically favorable for them to give up 2 electrons, hence becoming +2 charged ions. And because what they would be losing electrons and obtaining in terms of stability, that noble gas stability, that's why the alkaline earth metals typically only show a +2 charge. Once you get into the transition metal section, things start to get a little more variable because all of them are going to, with one exception, are going to show a +2 charge. And that's because, remember, the first electrons to go are the valence electrons. Well, before we get into the D block, our valence shell increases to the next level. So these S electrons are always going to be the first ones to go. So that's why the most common oxidation number that we see for the transition metals is +2. Beyond that, there's some patterns. We'll talk about them when we discuss transition metals a little bit later on. That will allow us to predict, what's the highest oxidation number that we might find, where, is there a general pattern to them. So again, we'll discuss these. As we move beyond that, once we get over to this section here where that stair-step line would be with the metalloids, I've got these labeled as like +3, for instance, in this column. And if you remember, the stair step starts up here. So boron is technically a metalloid, but everything from aluminum on down are metals, and metals typically lose their valence electrons because they have a loose hold on them. That's why they're classified as metals. So all of these are typically going to have a +3 charge. Okay. When we go to the next column over, the carbon family, this one is almost evenly divided between nonmetals and metals, and then you've got the metalloids in between. And you'll notice that there's more options here for the oxidation numbers. Okay. Mostly they seem to be positively charged, which means they're losing those electrons. So if you think about tin and lead, okay, and you ask yourself, well, how would they obtain a +2 charge? Well, tin and lead, their valence electrons are S2, P2. So the first step would be lose the p electrons. Well, if you lose 2 of them, that's a +2 charge. That would empty out the p valence shell, leaving you still with 2 in the valence shell. If those 2 were then lost, that would be a total of 4 electrons lost. So it's easy to see how tin and lead can typically carry either a +2 or a +4 form. The negative, that's really only going to apply for the elements that have more of a non-metallic characteristic to them. And so carbon, for instance, if it gains 4, hence a -4 charge, then it's going to have a configuration like neon. But if it loses 4, it'll have configuration like helium. So it can go either way, all right? And it really depends on what other element is carbon bonded to that's going to determine, is it going to gain electrons preferentially or lose electrons preferentially. So the negative charge really only applies to elements towards the top of this column. The positive applies more to the elements that are towards the bottom of this column. After you get past that, then it becomes more energetically favorable for electrons to be added to the elements to achieve that stability. For instance, nitrogen, you're looking at, for it to become like a full valence shell, it would either need to gain 3 to become like neon or lose 5 to end up like with helium. So it's more favorable, more likely that nitrogen is going to gain 3. Again, your stair-step line cuts right through this family, so towards the bottom, antimony sometimes will still show a -3, okay, but it will also show a +5, okay. That would be losing the 3p electrons as well as the valence s electrons, okay. But bismuth, all right, that's definitely underneath the stair step, definitely a metal. That one only shows +3 and +5. So again, a little bit of variability when you get into the section with the metalloids that are part of that. Continuing to the right, typically the oxygen family we think of as being -2. The halogen family we think of as being a -1. And then you have the noble gases with their naturally filled valence shell, so they typically take on 0 for your oxidation number. The lanthanide and actinide series down below, honestly, those the electron configurations there get a little more complex. They don't quite fit into our simplified way of thinking of Aufbau filling, and so typically we're going to see +3 for the lanthanide series, +3 or +4 for the actinide series. And to be perfectly honest, the chemistry that goes on with these elements is so similar because now you're talking about F electrons, which are buried well within the orbitals in the electron cloud. So it really doesn't play a whole lot into the chemistry per se because they're not really the exterior valence electrons. So it gets a little more difficult to get into the weeds of exactly why we've got +3 or +3 or +4. So for our purposes, just knowing that those are the typical charges we might see, that's going to be sufficient. We're not going to get into the weeds of exactly why at this level. So again, why exactly are those noble gases so stable? It has to do with their physical structure, specifically their electron structure. If we look at helium's configuration 1s2, it only has the first energy level. That's its valence shell, and s2 completely fills it. Neon, 1s2, 2s2, 2p6, the second main shell, its valence shell, is completely full. And for argon, we see the same thing with the 3s level. So what all of these noble gases have in common is they have a filled valence shell, which typically we'll hear referred to as a full octet. Kind of a misnomer when you talk about helium because it can't have 8 electrons, but it can be referred to as having a full valence shell. And so your elements, what charges, what oxidation numbers are going to take on, are driven by that the favorability of reaching a more stable configuration by picking up or losing electrons. Now, those transition metals, because of those partially occupied d sublevels, we get a number of interesting characteristics, one of which we've talked about already extensively, the fact that they can have multiple oxidation states, multiple charges. The second is that compounds of transition metals, in both solid form and in solution, tend to form brightly colored compounds or solutions. And this can be very helpful, particularly when it comes to identifying concentration of solutions. We can use spectrophotometry to be able to identify just how much of a transition metal compound is present in a solution by the fact that since it's colored, it's going to absorb certain wavelengths of light. And if we can measure just how much light is absorbed as it passes through a solution, we can measure what's the concentration of that because the two are directly related to each other. Your transition metals also exhibit some magnetic properties. Now, iron is a common one that we always think of as being magnetic, but your other transition metals can have some magnetic behavior to them. And we looked at this when we talked about paramagnetic configurations, diamagnetic configurations. Things that are paramagnetic are going to have unpaired electrons, and those unpaired electrons will interact with a magnetic field. Diamagnetic substances don't have any unpaired electrons and therefore won't be attracted to a magnetic field, and in fact they might actually be repelled slightly by magnetic fields. So when we look at the oxidation states and we consider the transition metals, so for the first row, the period 4 transition elements, these would be the ones in the 3D level. When they form cations, they're all going to lose their 4s electrons first. We know that. Okay? Valence electrons are the first to go. And so that means they're all going to have a +2 form, +2 oxidation state form, +2 cations. Scandium's the one exception because scandium being the very first element in that row, if the 2 electrons go from the 4s, well then it's got the 3d1 electron, and it's not just going to hang out on its own. So that one goes. Scandium typically only shows a +3 form. Everything else is +2. Beyond that, if you want to know, well, what's the highest my oxidation state can go? From scandium up to manganese, you can determine that maximum value by simply adding up how many s and d electrons do I have. Which means if you go to manganese, manganese ends in D5. So if manganese lost its 2 4s electrons and all of its d electrons, in other words, you're completely stripping off those last 2 energy sublevels, then you could have up to a +7 charge. Once you get past manganese, then the maximum oxidation number starts to decrease, because once you're past manganese, that half-filled D sublevel, now you've got, like for instance with iron, you've got D6. Well, it loses the 2 4s electrons, so that's +2. And then if it starts to lose d electrons, it loses 1, it ends up with a symmetrically half-filled sublevel, which is somewhat favorable from a stability standpoint. But then if you go and try and take any more than that, you disrupt that stable configuration. And energetically, there's no incentive to do that. So as you move past manganese, the oxidation number maximum starts to come down until you get to zinc, which only has the +2 charge, because zinc ends with 3d10. It's completely filled. It may lose the outer valence electrons, but then beyond that, if you take another electron away, you're eliminating a symmetrically filled sublevel configuration. And again, energetically, there's no incentive for that to occur naturally. So we mentioned iron before. We kind of already talked about this question. What oxidation states would you predict to be the most common for iron? So to answer a question like this, you want to start with the electron configuration for the element itself, and then ask yourself, okay, if it's going to lose electrons, where are they coming from first, and how many is it likely to lose, since it's a metal? Well, the 4s electrons, okay, so that's 2 of them, that would lead to a +2 charge. But the other common, and actually the most common form that we see for iron, is in fact +3. Well, the +2 charge results from the 2 4s electrons being lost. And when a single 3d electron, which would be that d6 electron, is lost in addition to that, that's 3 lost, so hence +3. But in losing that single 3d electron, now you end up with a configuration that has a symmetrically half-filled d sublevel, which has a certain degree of higher stability associated with it. All right, think about niobium. We don't typically talk about niobium a whole lot, but if we consider what oxidation state would we predict to be the most common for niobium and why? Well, niobium's configuration ends with 5s2, 4d3. Okay, so we might expect +2 because it's going to lose the 2s electrons, but then those 3d electrons, okay, d3 is no special configuration there. And if it loses just 3 more electrons, well, now it's completely lost that outer valence shell, and it ends up with 3s2, 3p6, a noble gas core configuration. So it's highly likely that niobium is going to lose all 5 electrons, and hence we would predict a 5+ charge for niobium. The last question here is, why doesn't titanium 5 exist? Titanium with a +5 charge. And so if we start with titanium's original configuration, it ends with 4s2, 3d2. Well, if it loses 2 electrons, that'd be the 4s. If it loses the d electrons, that'd be a total of 4 lost. And at that point, it would have a noble gas core configuration. So to lose a 5th electron would be to disrupt a filled valence shell. And that is really not energetically likely to happen at all. And so for that reason, we are not going to naturally see titanium-5 ions existing, because the amount of energy it would require to remove one electron from a valence shell configuration, it would take extreme conditions, and it's not likely to occur at all.